Hello again, it's Mr. LaBeouf. In a previous video this week, we looked at the three basic rules of exponents. Our goal was to expand our understanding of exponents so that we can raise a number to a power other than a natural number. 4 to the third power is 4 times 4 times 4. The 3 there, the exponent of 3, is a natural number. In the previous video, we expanded just slightly our understanding of exponents by realizing that when you raise a number to the 0 power, as long as you're not raising 0 to that power, any number other than 0 raised to the 0 power, strangely enough, is not 0, it's 1. We explained in the previous video why that's true. In this video, we're going to expand our understanding of the exponent n to all of the integers, including negative integers. A quick review of the three basic rules of exponents is important here. We're going to particularly use rule number 2 in our understanding of negative exponents. Let's just go through an example of each one of these rules again to refresh our memories. Rule number 1 tells us that if we have to evaluate x to the third times x to the fourth, we add the exponents. And the reason for that is very clear. This is x times x times x times 4 x's multiplied together. So we're going to have a total of 7 x's multiplied together. Rule number 1 tells us that we can add the exponents and get x to the 7th. Now, a quick word here about the x's. These big numbers here, the numbers that are being raised to a power, they're called the bases. This rule only works when the base is the same. So, for example, 5 to the third power times 5 to the fourth power will be 5 to the seventh power. But if we have 5 to the third power times 6 to the fourth power, there's no way to simplify that. The only thing we could do was evaluate 5 to the third, which is 125, and multiply that times whatever 6 to the fourth is. And this would be a pretty big number, as is 5 to the seventh. This is bigger. But the point is that because the bases are the same, because the bases are not the same, because they're different, we can't simplify this other than to work it out. So just an emphasis on the fact that these two x's here are the same number. Now, as far as rule number 2 is concerned, let me make up an example that looks similar to number 1, but is completely different. Let's take x to the third power and raise that number to the fourth power. And this is rule number 2. Rule number 2 tells us that in this situation, we multiply the exponents. So I'll write the result here. X to the 3 times 4, which is x to the 12th. And notice it's a different result. Now, I've said all along that rule number 1 is basic. It's obvious. It really goes to the heart of what we learn as very young students, as 5th graders, about how exponents work. As far as rule number 2 is concerned, it's almost as easy because you can revert back to rule number 1. What does it mean to raise a number to the fourth power? We have to start there, understand what that is. Well, it means multiply 4 of those numbers together. And what is the number we're raising to the fourth power? It's x to the third. So what I wrote here originally is nothing more than an abbreviation for this. X to the third times x to the third times x to the third times x to the third. 4 of them. Now, this situation can take us back to rule number 1. Now, rule number 1 only has 2 powers of x multiplied together, but it can be extended to any number of those. What does this mean, x to the third? It's 3 x's multiplied together, and then another 3, another 3, and another 3. Make sure you realize, before you go on, that what this is representing here is a total of 12 x's being multiplied together. 3, 6, 9, 12. I'm not going to write them all out. You can picture it. So that brings us to the result we got through the shortcut of multiplying 3 times 4. It brings us to x to the 12th. So rule number 2, it's a different situation, but your understanding of it can bring you back to rule number 1. And it also should be easy to understand. In the future, if you're faced with one of these two situations, what I tell my students frequently is don't flip a coin. You might say to yourself, well, I know I have to either add or multiply the exponents. Well, just think it through. It makes sense here to add the exponents. Here, it makes sense to multiply them. Think it through and figure it out based on what these rules mean. Now, as far as rule number 3 is concerned, if we just take a case like this, we have the parentheses are indicating to us that it's not just the y that's being raised to the 4th power. If we didn't have the parentheses, our understanding of things would say that this is x times y to the 4th. And there's no way to simplify that. If we knew what x was and what y was, we could work it out. But this is saying x times y to the 4th. Without the parentheses, we understand that only the y is being raised to the 4th power. The order of operations tells us this. Tells us that. Evaluate y to the 4th first and then multiply by x. But with the parentheses, it's different. The parentheses is indicating that the entire x times y is being raised to the 4th. So what would that look like? Well, it would be xy times xy times xy times xy. I won't put any raised dots there. This indicates multiplication. And multiplication is commutative and associative, meaning that if we're multiplying a bunch of numbers together, we can do it in any way we want. So why not regroup these as x times x times x times x times y times y times y times y. 4x's multiplied together times 4y's multiplied together. And of course, we can abbreviate this as x to the 4th times y to the 4th. 4x's multiplied together, 4y's multiplied together. As you look at the rule stated out here, you're applying you're raising the x to the 4th power and raising the y to the 4th power and multiplying those two results together. And it's the parentheses that tells us to raise both of these to the 4th power. That's rule number 3. So now we're going to move on to an understanding of raising a number to a negative integer power. The integers can be represented like this. They go on forever to the left, they go on forever to the right, and it is the collection of the natural numbers. Remember, the natural numbers are 1, 2, 3, 4, 5, and so on, plus 0. And there is a name for a collection of numbers that includes the natural numbers and 0. They're called the whole numbers, and these are the numbers that we work with when we're very young. When we're very young, we need 0 to do things like 4 minus 4 or 0 plus 4. The whole numbers are what we operate with when we're very young math students. And then when we get into middle school, or a little earlier maybe, we realize that there are the opposites of the natural numbers. 0 is its own opposite, of course. And then if you include, along with the whole numbers, the opposites of the natural numbers, -1, -2, -3, and so on, you have what are known as the integers. We have already seen what it means to raise a number to the 0 power. So that leaves, what does it mean to raise a number to the -1 power or the -2 power, and so on. And we'll start with -1. There's a special meaning for raising a number to the -1 power. That's what we'll look at first. But before we do that, there is a little bit of a loose end that I need to clear up at this point. What do you suppose that's equal to? Now, we talked earlier when we were exploring raising a number to the 0 power that we explained why we have to see 3 to the 0 power as 1. And I use the phrase there, counterintuitive. It is counterintuitive that 3 to the 0 is 1, but it's true. Because it has to be. This one here, if you were thinking earlier, well, I think it's 3, but I don't know, because we had this weird situation here. Well, 3 to the 1 is intuitive. It is what you would expect it to be. 3 to the 1 power is 3. For a long time, I just sort of accepted that and didn't bother explaining it, just assumed that the students would realize 3 to the 1 is 3. But in math, you should always be looking for a way to justify something, a way to explain it or to prove why it's true. Always try to be looking for the why of something. Well, you can actually show based on rule number 1 why raising a number to the 1 power is the number. It's very simple. Take 3 times 3 times 3 times 3. Now, by the definition of exponents that we all learn when we're very young, this is, of course, 3 to the 4th power. Well, what if we substitute for each of these 3's 3 to the 1 power? So 3 to the 1 times 3 to the 1 times 3 to the 1 times 3 to the 1. And think back about rule number 1. Rule number 1 says that when you're multiplying powers of, in this case, 3, add the exponents. So rule number 1 would tell us that this is 3 to the 1 plus 1 plus 1 plus 1, which is 3 to the 4th. So 3 is the same as 3 to the 1 because 3 to the 1 works out according to rule number 1 when we substitute it for 3. That was a little bit of a loose end that had to be tied up before I introduce raising a number to the negative 1 power. So let's do that now. Let's consider 3 to the negative 1 power. And the first thing I want to say about negative exponents, this is so important. The negative exponent has nothing to do with the sign of the number. That's a little hard to get used to for young students. There's a negative sign here, but this number is positive. If I put a negative sign out here in front of the 3 to the negative 1, then it would be a negative number. But this is a positive number. The sign of the exponent has nothing to do with the sign of the number itself. So please keep that in mind. And to arrive at a conclusion of what 3 to the negative 1 has to be, let's do this. Let's multiply it by 3 and see what happens. Well, we just looked at the fact that 3 is the same as 3 to the 1. So I can put a 1 there. And rule number 1 tells us to add the exponents. So think about what 3 to the negative 1 times 3, or 3 to the negative 1 times 3 to the 1 would have to be. You're right. It has to be 3 to the 0 based on rule number 1, because we add the exponents. 3 to the negative 1 plus 1, or 3 to the 0. We've already established that 3 to the 0 is 1. And this is how math works. Once you establish something, you use it to establish other things. It's a progression. So let me rewrite this as 3 to the negative 1 times 3 equals 1. Because 3 to the 1 is 3, and 3 to the 0 is 1. So look at what we have here. A number times 3 is 1. What is the number that we multiply 3 by to get 1? You should know. It's 1/3, which is known as the reciprocal of 3. 1/3 is the reciprocal of 3. So this has to be 1/3 times 3. 3 to the negative 1 times 3. We just showed based on rule number 1 that this has to be 1. And so the 3 to the negative 1 has to be 1/3. And that is the key to raising a number to the negative 1 power. That's what it means. You get the reciprocal of the number. Unless, once again, we have to exclude 0 because 0 has no reciprocal. So this number here, 0, to the negative 1 power. 0 to the negative 1 power is undefined because it would be the reciprocal of 0, which doesn't exist. So we'll close this video for now, and then in the next one, we'll explore some of the other negative integer exponents. We've already established what 3 to the negative 1 is. Bye-bye.